Should we start? No?
Not yet.
Yes?
Not yet.
Not yet. Something's being fixed.
No, it's just
usually went to the side, but
it's a bit sick.
Yes. Good afternoon, PCS members and friends. Today we have an Institute for Basic Science Physics colloquium, and our scientific host today is Professor Rodolfo Del Campo, who will introduce our speaker.
So welcome everyone. So it's really a great pleasure to introduce Marin Bukov. He's currently a research group leader at the Max Planck Institute of Complex Systems in Dresden. And he has a spectacular CV. I was just reading it. It's beautiful because since very early on as an undergrad, had already some amazing supervisors. So I read he started working with Stefan Kerin, that many of you will know for his book on flow equations. He later on worked with Laszlo Erdős, who I know very well for his work on random matrix theory. He also worked with Emmanuel Bloch and Claude Paulet on ultra-cold atoms. And then he started his PhD at Boston University with Anatoly Polkovnikov, who will be here later on this week, we hope.
Don't get wait.
Yeah, it's wonderful.
Somewhere in the air.
Yeah, so Marin was also a postdoc at the University of California in Berkeley, working with Norman Yao and Udo Dahlmann, who I both greatly admire. And after that, he went back to Sofia, to Bulgaria, as a research group leader. He stayed for a while. He got one, I noticed, well, get it right, Astanasov President Award from the President of Bulgaria for his research on the borderline between machine learning and quantum technologies, for which Marin Bukov is widely recognized as being a pioneer. And well, currently he's, as I said, at Max Planck Institute. So we know Marin for many different research lines. I mentioned the interface of machine learning reinforcement learning with, in general, quantum technologies, but also in particular in the context of the conference we are hosting on quantum computing complexity and control. He also did a pioneering work in machine learning with counterdiabatic deriving that inspired many other researchers in the community. And there are other research that he has been doing, but today he is going to be talking about periodic deriving, which is a topic which is, I understand, close to his heart because he already in his bachelor thesis, he already did some of that. Yeah. So yeah, Marin, whenever you want. Thanks a lot.
Yes. Thanks a lot, Adolfo, for the other organizers for having me here. It's a great event. It's my first time here in Korea, and I so far enjoy it a lot. It's also the first time that I'm given so much speaker time at the workshop. So there's the colloquium today, and tomorrow there's going to be another shorter talk on this. And indeed, I like working at the intersection of different fields. And when I was thinking about what to speak about today, I think, given the control as being one of the major topics of the conference this week, I decided to talk about the control of quantum simulators, and in particular, the relation to periodically driven systems. So today and tomorrow, you'll hear a lot about shortcuts to adiabaticity and counterdiabatic driving for periodically driven systems now. And hopefully you'll find some new inspirations and some new ideas there. So this is supposed to be a colloquium, so I will try to make it accessible to a broad audience. There is, of course, going to be the first part of the colloquium that is going to be I'll try to do it intuitively and without many equations, but then towards the second part of the talk, I also have some slides that hopefully will be appreciated by the experts who already know these things well. But I wanted to say, you guys should feel free to stop me and ask questions anytime. It's not the idea that I go through, a bunch of slides, but that you kind of get the message and the idea here. So don't hesitate to stop me anytime you want. All right. So today's topic is going to be about periodically driven systems, and in particular, how to use periodic drives as a toolbox for quantum simulation. And many of you have heard about quantum computing these days. It's quite popular. Also, quantum simulators are very popular. And I want to start by actually distinguishing, simulators from computers so that you guys know what we're talking about. And to do this, I'm going to bring you back all the way to 2nd century before Christ, to ancient Greece. This is basically an interesting discovery. So the so-called anti-theorem mechanism was found close to this island of Crete here. You can kind of see where it is. So at the bottom of the sea in a shipwreck, and it was found about 100 years ago. And this is roughly how this original device actually looked like. So you can see it's quite rusty, but you can already recognize like some gearing wheels there. So this was obviously some machine that was doing something interesting. And historians actually figured out what it was doing. They even tried to reconstruct. This is kind of a modern reconstruction of this. And so when they announced the discovery to the media back in the day, all the headlines immediately said, the first ever computer from the ancient days, right? But if you actually look very closely into what this device is doing, you'll realize it's actually not the computer for the following reason. So this was an ancient model for the solar system, and that's 200 years before Christ. So that's the solar system the way the ancients understood it. So the sun wasn't even at the center of it at the time, right? But the Earth was at the center of it in their understanding. And nevertheless, they figured out how to do interesting mathematics and astronomy, and to predict the motion, for instance, of the moon and the sun. And this gadget here, the anti-theorem mechanism, was able to predict eclipses. They were quite advanced at the time, so they were the gods, right? Maybe it was Zeus, right, that was commissioning the eclipses, right? But they were able to kind of predict where they came from. And one thing, and the reason actually why I'm mentioning this mechanism here, was because you can kind of see this is maybe not the first computer, but it's definitely one of the first simulators that humankind developed. And it's a simulator because it can only simulate the behavior of this particular system, the solar system. And it is not universal. So you won't be able to use this device in order to compute anything you want, right? But only to predict like certain types of events. And so I want to use this in order to emphasize the difference between computers and simulators. So computers are universal. You can compute anything with them, at least in principle, that you want. Whereas simulators are specialized and therefore non-universal. And so when we talk about quantum simulators, we will be thinking about devices like this anti-theorem mechanism that allow us to simulate the behavior of physical systems. And because it's going to be quantum simulators, these would be quantum devices from which we will be learning something about other quantum systems. So that's the idea. And as at this stage, you might wonder, well, aren't computers just more powerful, right? Like, so why should we care about simulators at all? Well, it turns out that it's very difficult to build, like a universal computer, right? So it took humankind, 2,000 more years, maybe 2,020 more years in order to get, to a universal computer, whereas simulators are there and they're a little bit more accessible. Nevertheless, if you take quantum simulation seriously and simulation in general, then the first thing that you want from your simulator is to make it, as widely applicable as possible. So, it could be one device, but then you would want with a single device to kind of flip this constraint as much as you can and simulate as many other physical phenomena as you can. It's not going to be universal, but you still want to enlarge its applicability. And what this talk is going to be about is the use of non-equilibrium periodic drives in order to change the behavior of systems in such a way that you can simulate interesting physics. And so I want to introduce here a couple of examples. So what you see on the left is a so-called Kapitsa pendulum, which has a stable equilibrium point and then an unstable equilibrium point at the inverted position. So you can kind of see it's kind of a trivial, boring classical mechanics system. And now what's going to happen is the pivot point is going to get shaken vertically at a very, very high frequency. And you can't see it here, but this is actually a frequency generator. So now maybe you can see the vibration. And once the frequency becomes high enough, you can actually change the behavior of the system completely. And so what you can see is not only can you stabilize the inverted equilibrium, but this behavior is also stable to small perturbations. And so the idea here is that you can use a periodic drive in order to completely change the behavior of this simple physical system. Of course, all of this relies on a high-frequency periodic drive. So at the moment the frequency becomes lower than a certain critical value, then the pendulum drops down. It can no longer sustain the equilibrium at the inverted and then you can see, without the drive, it's still literally the boring pendulum. So this is one example of how you can use periodic drives in order to enhance the capabilities of mechanical systems. So here's another example here that you can see, the so-called rotating saddle. So you can see this is a saddle. You can think of it as a potential for this particle here, like this fairly large, like this large like balloon ball. And so what this guy from Harvard is demonstrating is that basically the saddle is unstable because the tiniest of the perturbation takes the particle and allows it to tip over. So now what he's doing here is he's again using a high frequency periodic modulation of the saddle. And what this actually allows, in this case, to do is to stabilize the behavior of that particle. So you can kind of see that using periodic motion now can turn unstable saddles to something that is effectively stable. And this oscillation, this stability again depends on the oscillation, on the frequency of this. And it's a phenomenon that can be understood in pretty much the same way as the Kapitsa pendulum, as I will show you later on. In fact, I'll explain in a second that this very simple idea actually was, important enough to give you a Nobel Prize for the so-called pole trap. So I'll come to this in a second. So it looks like very, very simple, but actually people were quite impressed when this came about. And so basically today's talk would be about using this very simple principle from classical physics to then lift it to quantum mechanics in order to do quantum simulation with periodic drives. Yes, please.
Just one question. I think initially when the ball on top of the saddle, put a spin on it. Was it necessary to make it stable? Just put it like that.
If you consider an extended object, then yes. If you think about a point particle, then no. Okay, and we're thinking about point particles. It's just in this case, it was having like an extended object which also has like moment of inertia, etc., etc. You can also see that there's an oscillation that damps away, right? So even if you have like a little bit of noise in the beginning, that's actually fine. So now it's damped away. Okay, yeah, keep these questions coming.
Well, the ball eventually falls off. So in this video,
that's because the frequency becomes lower than a critical frequency that supports this stable equilibrium.
So it's not a general phenomena that the stability of the equilibrium is it's quasi-stable in some sense. It's just for a long time period it's stable, and then.
So if you keep the frequency high enough, that will be stable forever for that single particle. It's a little bit more complicated, more interesting when we get to many-body systems, in particular many-body quantum systems, and you'll get there in the second part of the talk, and we'll discuss what's going on there in terms of stability.
Okay, thanks.
All right, good. So now that I've basically shown you the idea, the basic mechanism behind the use of periodic drives, the question is now, how do we actually make this a toolbox for quantum simulation? And so today, hopefully there will be time to discuss three different pillars of this toolbox. The first one is the use of periodic drives for quantum engineering. The second one is precisely the question that was brought up just a second ago. Are these actually systems, these states, stable or metastable, and what happens there? And finally, in light of this workshop, and this is actually going to be the larger part of the colloquium, we'll talk about how to control and manipulate these systems that are exposed to these high-frequency periodic drives. So we will be using the drives in order to stabilize interesting states, and then the question is, how do we actually control the states, right? So what do we do with them? All right. So first things first, let's talk about quantum engineering. And so over the last decade, at least, but even earlier than that, periodic drives have become instrumental for the engineering of quantum matter. And so here are a few examples that I now want to go over with you slowly together so that you can appreciate, what actually in the quantum world people have done using these periodic drives. So the first phenomenon is the dynamical localization phenomenon. So this is my picture of the point particle in the saddle. And as I alluded to a few seconds ago, there's a very interesting application in this setup in order to trap ions. So you have heard of this quantum computing platform, or quantum simulation platform as well, which is called trapped ions, where people cool down charged ions to very low temperatures. And then the question is, can you actually trap them? And you want to trap them because this is how you can start manipulating them. If you can trap individual ions, then you might be able to actually control the interactions between them. You might be able to do like a simulation with them or a computation with them. But there's one problem. Suppose that you have a charged particle and you want to design such a potential for this charged particle such that it stays at the bottom of the potential and it never moves, right, from there. But the particle is charged. Well, the fact is that, Maxwell's equations actually constrain us a lot in doing this, because we know that away from where this point particle is situated, the potential, the electrostatic potential, is actually going to obey the Laplace equation, right? So there's no charges away from where the particle is situated. And so if you try with such a static or DC field to construct a trapping potential for a charged particle, you'll see that this is not possible, because a trapping potential requires that you have a minimum. That is to say that the first derivative of the potential vanishes, but it has to be a minimum. So it means that the second derivative has to be positive, right? Whereas Laplace's equation says that the second derivative is identically equal to 0, and therefore it's necessarily a saddle, right? And so this is the reason why you cannot use static or DC fields in order to trap individual charged particles. And this was a big problem, in this field of trapped ions. And so what eventually Paul did in 1989, I think it's hidden here, is he figured out that by using these high-frequency periodic drives, it's actually possible in pretty much the same way that I just showed you to trap a charged particle. So he found a way how to avoid this no-go theorem by Earnshaw, and this actually gave him the Nobel Prize a couple of years later. So this mechanism is a fundamental mechanism, for instance, in trapped ions. But that's not the only example of so-called dynamical localization. Here's another experiment from a group in Italy, where what they did was they used the high-frequency periodic modulation in order to tune the tunneling matrix element of a particle in an optical lattice. So imagine that you have an optical lattice. You create these typically by shining laser beams. In this optical lattice, you can have now neutral atoms. Neutral atoms can easily be trapped in these potentials, but then these atoms are going to hop, like shown here by these arrows, and they're going to hop between minima of this potential. And what is actually happening there is that the particles tunnel quantum mechanically through this potential barrier. However, one problem with these systems is that what you want to do with them is you want to simulate the behavior of many body interacting systems, and in particular phase transitions. And the paramagnetic example, for instance, can be a Hubbard model, where if you have two particles to come on top of each other, two bosonic particles, for instance, then require interaction energy. So at very strong interactions, you don't want the particle to be, the energy doesn't let particles come on top of each other. And at very weak interactions, the particles hop and they delocalize over the full system. And this leads to a phase transition between a superfluid for weak interactions and the mod insulator for strong interactions. The question is now, how do you actually observe this in the lab? And of course, people have figured out a way how to observe this by using magnetic fields through so-called flashback resonances to control the strength of the interaction. But that's actually a fairly complicated procedure, and it requires specific types of atoms to do that. So as an experimentalist, you would want your quantum simulator to be a little bit more versatile and to be able to control independently the ratio between the interaction and the hopping. And one way to do that is to use a high-frequency periodic drive. Now, this is not something that you can see easily from the picture, but the idea is that if you apply a high-frequency periodic drive in a specific way, in pretty much the same way that you can stabilize, the saddle, what can happen is you can use destructive interference to suppress the tunneling between neighboring lattice sites, whereas you keep the interaction strength intact. And so imagine that you have a system now in your lab where you cannot control your interactions, but you can use the periodic drive to control your tunneling. And so effectively, you can tune the ratio between the interaction and the tunneling, which is the parameter that controls the phase transition. And what this group in Italy has done, and this is experimental data here, is literally they have measured this effective tunneling matrix element as, in the presence of the periodic drive as a function of the amplitude of the drive. And what they can see is that this function is a kind of a Bessel function that has like a 0, right? And the two curves here, one is a sinusoidal shaking and the other one is a different kind of shaking, which is basically a square wave drive. This is just to show that the mechanism is relatively robust. And so very close to this 0 of this tunneling matrix element, the system undergoes a phase transition and becomes strongly interacting, and they have observed the multisyllated transition.
So in this cancellation of pendulum,
Yes.
I am not able to appreciate why it needs to be periodic. You can do some other kind of thing and still get things to cancel. Is that possible?
I don't know how to do this. Maybe you do. So the idea is that if you don't allow yourself to touch, like the interaction strength, right? And you cannot touch the tunneling. So the only thing you can do with the tunneling is you can crank up, like the lattice and make it like very deep, right? But this automatically affects, both the interaction and the tunneling. So you have to be very careful to see what's going on there. If you want to have conditions that are equal and set, then maybe there's a different kind of drive that would achieve a similar cancellation, but they don't know it, right? And this is one way to achieve this. Yes.
I think the first picture, we think the method is equivalent or different from this so-called time average tension.
It is very similar, and I will show you in a couple of slides that if you actually go into the theory behind this mechanism, then the time average potential is essentially the first order approximation that you get into the description of this physics. Yes, so your intuition is pretty much spot on. Yes. Yes.
I use the graph. Can you some numbers about the frequencies of these high frequency noise?
So yes, and this is something that I better said right now. So typically, we talk about like high frequency limits, etc. But in physics, limits don't exist in nature, right? So limits only exist like pen on paper. So what I typically mean is that the frequency is 10 times larger than the pair hopping and interaction strength, right? So if the hopping is something like 1 kilohertz in that experiment, then the frequency has to be 10 kilohertz, and all of this is pretty much within the experimental, the range of the experimental platform, and that's why they have tracking. All right. Sorry.
Okay, ask a short question. Can you tune, for example, the next nearest neighbor hopping and the nearest neighbor hopping individually?
You might be able to do this if you have two different drives at two different frequencies, right? Because then you would have essentially two coupling parameters, two amplitudes, and then there will be a resulting more complicated function that will have a 0, and most likely the 0 will be different for the two parameters. So one thing you can do is you can fully suppress the nearest neighbor hopping, which would otherwise be dominant, and then exhibit the physics or reveal the physics of the next nearest neighbor hopping in this way.
Nice.
You have to be careful because in the presence of interactions, you also get the so-called interaction-dependent hopping terms through this behavior, where one particle would hop to its nearest neighbor, interact there, and then hop back, and that would be a virtual process that would essentially renormalize the energy of your local one-side potential. So yeah, you can do these things, but you have to know how to do this. You have to play a little bit with it.
Thank you. How do we implement what kind of gradual stabilize the system?
This is the art of Floquet engineering. So this is basically where I'm. But it's a highly non-trivial question, and not all drives do the job, and you have to know what you're doing. But I'll give you a very simple way to think about it. Okay, so that was the very first example. Now let's switch gears a little bit. So the second example is the example of so-called artificial gauge fields. And so this is an example where you take a lattice of electrons, right? So this is the system that we want to simulate. This is a solid state system with a square lattice with electrons on it, 3 electrons. So we're going to turn off the interaction, but we're going to pierce the lattice with a strong magnetic field. And this actually is very interesting because it is described by the so-called quantum Hall effect physics. The problem, however, is that if you have a real material and you apply a magnetic field, then the relevant quantity is actually the magnetic flux per plaquette, per square plaquette. And it turns out that in order to get this flux to be sufficiently large, right, in order to study like the strongly interacting physics between the electron and the magnetic field, then it requires magnetic fields on the order of 10 to 100 Tesla. And that's pretty much basically, the biggest we can do. But with 10 to 100 Tesla, you basically get only a fraction of the flux quantum. And so you're only able to access this very small part, basically, of the parameter space of your system. And Hofstadter in the 1970s actually solved the problem theoretically, and what he came up with is the spectrum of that simple system, an electron in a magnetic field on a square lattice, as a function of the flux quantum. And as you guys know from quantum mechanics, the flux quantum is a number that can basically go between 0 and 2 pi. So I have normalized it here by the flux quantum, right? And so there's like a full diagram, which is fractal, and it is known as the Hofstadter butterfly that you would like to investigate the physics of, but you actually don't have, an experimental system that can realize this. And so the idea now is to use periodic drives in order to gain access over the physics in this diagram. And the question is, how do we do this? But there's a big issue here, if you think about it, because electrons in magnetic fields, just think about them classically, they undergo cyclotron orbits, right? So there's like these orbital orbits, orbital effects. And these orbital effects occur because the electrons are charged particles that, feel the magnetic field. And whenever you have, one of these cold atoms systems for quantum simulation, you know that atoms are actually neutral, so they're not charged. And so atoms will never coupled to any magnetic field you would, any orbital magnetic field that you would basically apply to them, right? So you won't see them, You might see that there's a hyperfine splitting if you set up the magnetic field, but it will not couple to their motion in any way because they're charge neutral. And so the question is now, how do we do that? And one idea to do this with optical lattices is to use very strong periodic drives. And in this case, what you need in order to simulate the physics of a magnetic field is you need a drive that actually breaks time reversal symmetry, because you know that magnetic fields break time reversal symmetry. And such a drive can be like a circularly polarized drive. For instance, a light that couples in this lattice, in this space xy, which is square lattice space, in a circular way. And it turns out that if you do that, you can actually realize precisely this model of a particle in a magnetic field, and so you can study Hall effect physics way, way above this threshold here that is set by the largest possible accessible magnetic fields these days. And in fact, in the experiment, they were able to do like flux quanta as large as 1.5 pretty much everywhere. This is because the strength of the effective flux that you get in units of the flux quantum in this problem is actually set by the phase of the drive, right? So it's the phase of the drive that gets transformed into an Aharonov-Bohm phase, right? Or into this flux phase. And it's actually the relative phase between, the X and the Y component of the drive, because we have like a circular drive, so they are a phase, you can kill that. So this is another example. And actually, closely related to this example of an artificial gauge field is a so-called topological matter. And this is again, the same example. So it turns out, as many of you probably know here, that the energy bands that describe the behavior of a single electron in the presence of a magnetic field on a lattice actually have non-trivial topology, so one can associate with them so-called Chern numbers that would tell you precisely how you get transversal responses when you apply an external force in the presence of that field. And so all of this physics actually has been investigated experimentally. So there are many groups here which have contributed to this. So this has been now measured in the lab over the last 10 years. So using periodic drives, they have managed to access regimes that are completely inaccessible in conventional solid-state materials. So again, we use one quantum system, in this case, these ultra-cold atoms, to learn about the physics of another quantum system that we cannot actually investigate. Of course, where this is all going now and where this is getting more interesting and more exciting is in the regime of strong interactions between these so-called electrons, which leads to a so-called fractional quantum Hall effect. And this is much more difficult to understand theoretically because you cannot solve it and you can also not simulate it easily, especially when you have like many particles. And this is where quantum simulation is potentially going to be one way to address this problem. So this is where we want to go with that. All right. So now these are kind of, examples of periodic drives that emulate phenomena that we know exist in equilibrium systems, right? But we just cannot access them in the lab, right? But you can also use periodic drives in order to create entirely new type of states that do not exist in equilibrium. And one example that you might have heard about is the example of a so-called time crystal. I won't go into the details of this today, but I will speak a little bit about it tomorrow. But just for those who are unfamiliar with this, the idea here is that these periodic drives are periodic, and therefore they have a discrete time translation symmetry. Now, your system of spins might have another kind of symmetry, for instance, an Ising Z2 symmetry. And what can happen is that you can break a combination of these two symmetries together. And when you do that, due to symmetry breaking, you actually get a new form of order. And this order does not have an equilibrium counterpart because the symmetry breaking involves part of the symmetry which is actually dynamical, which comes from the periodic drive. And so whenever this happens, in this specific case of a Z2 symmetry, for the periodic drive and for the spins, this leads to a so-called time crystalline ordered state. And these states have been measured in experiments. The idea is that you prepare your system in a polarized state, and then you apply the periodic drive to it, and then you wait for one driving period, and what you see is that your state basically flips. But then if you wait a little bit longer for a second period, then the state comes back to itself. So it's something like a clock. It goes up and down, up and down, up and down. And the whole point is that this is actually stable to perturbations. It's stable to perturbations in the drive. It's stable to perturbations in the interaction strength. It's actually stabilized by interaction. So it's a genuine new type of order. So this is just one example of what you can do with these systems. That is not just an emulation of some equilibrium theories. Now, I need to speed up a little bit. So beyond quantum simulation, there's quantum computing. Maybe the most interesting example of application of periodic drives to quantum computing is the simulation of dynamics. So some of you might have heard about rotorization. So this is basically a way to simulate the dynamics of a static Hamiltonian in terms of a circuit, which, as you can see here, repeats periodically and is therefore a periodically driven systems. And I'll show you some examples of how this is related to the stability of these states. And last but not least, there are applications in quantum sensing where, for instance, people use so-called dynamical decoupling sequences to control them and to stabilize the polarizations of these systems. So what you have to know here, what you have to notice is that these are again type of periodic sequences that one can apply to your nuclear states to stabilize them. And so after this very long introduction of what you can do with these periodic driven systems, the question is where do the engineering capabilities actually come from, right? So how do we actually do this in practice? And to do this, I'm going to bring you back to late 19th century France, where physicists, or I think they were called maybe natural philosophers at the time, right, were interested in the study of the nonlinear dynamics of simple, mechanical systems. Like, for instance, the van der Pol oscillator, whose dynamics is described by this nonlinear equation of motion here, and whose phase-phase dynamics I've shown here in this portrait. And one thing that you should see here is this very special red orbit, which is a stable orbit. It's a so-called separatrix. It's very important in the discussion of the stability of this pendulum, because whenever you initialize the pendulum, if you follow the arrows, you see that it tends to flow towards the stable orbit. But so if you take a system of nonlinear differential equations, and if you linearize it along the stable orbit, what you end up with is a linear system with time periodic coefficients. And in 1883, Floquet showed that the time evolution operator for this system actually factorizes into two parts. On the one hand, you have the so-called micromotion, which is periodic with the same period as the linearized drive. But then there's an additional part, which is generated by the so-called Floquet Hamiltonian. And one thing you have to note here is that this operator is independent of time. So even though you started with some time dependent system and you would expect some very complicated evolution, in fact, because the dependence is periodic in time, you actually have some structure in it. Now, this is the theorem. It's very similar to Bloch's theorem. Actually, Bloch proved the same theorem about 50 years later. But whenever somebody shows you a theorem, a mathematical theorem in physics, then the first question you should ask them is, what is the physics of it?
It separates two basins of attraction.
That's right.
In that picture, everything is getting attracted to that plot there.
Yeah, so
what is it separating?
my guess is that there are points that basically live outside outside like what's shown here, right? So they're probably points in.
Is it separatrix or is it a limit site?
Okay, it might be that it's not separated, but it's yes, you're right. Yes, that is a limit site. Thanks for this correction. Yes, that's important. Yes, exactly. In this case, it's a limit site. But now going back to the theorem, so the question that we should ask at this point is, what's the physical meaning of that here, right? So it's fine, I'm introducing some object, but what do they do? And the idea is that physically you can interpret Floquet's theorem in the following way. So it basically tells us that there exists a distinct rotating frame, which is described by this micromotion operator. And if you go to that rotating frame, then the dynamics is governed at any time by this time-independent Floquet Hamiltonian. And so from your intuition, however, you know that rotating frames, there's something funky about them. They are non-inertial frames. And in particular, they have these fictitious forces that are there, right? For instance, the centrifugal force or the Coriolis force, these are examples of these non-inertial forces. And so whenever somebody tells you that they're actually doing Floquet engineering, what they're secretly doing is they're looking for the rotating frame where the dynamics of the system exposed to these fictitious forces is actually described by a Hamiltonian that they want to engineer. So for instance, if you think about these neutral atoms in the magnetic field, and you look at just the Lorentz force that you want to emulate, which essentially gives rise to the classical dynamics of the system, and you compare it to the Coriolis force that you experience on the merry-go-round, you see the similarity in the structure of these forces, where the magnetic field is essentially generated through this rotational motion, right? So that's the basic idea behind Floquet engineering. So you basically are looking for a special rotating frame, but you want to engineer this rotating frame in a way as to find the physics that you want to study. And that's non-trivial. For this, you actually need to know how, to have an idea, to have an intuition, to know physics, right? And how things relate.
But in particular system for this rotating frames, like affect each other to unstabilize.
So we'll talk about stability in a second. Yes, but this can also be done in many body systems, and you can actually get these effects for very, very, very long times to be stable. So they only become unstable immediately. Okay, all right. So now a little bit more formally, here's the Floquet eigenvalue problem. So you basically have eigenstates and eigenenergies. One thing that's important is that the Floquet energies are only defined up to integer multiples of the driving frequency up to these shifts, and that's because these energies basically live inside the exponential, and the exponential is going to round them around. And one question now is, how do we find this effective Hamiltonian, right? And the standard way to do that is to try and basically solve Schrödinger equation. But the problem is that exact solutions are quite limited because you're solving a time-dependent problem. And so besides some circularly polarized drive or maybe some harmonic oscillators, it's very difficult to find a way to solve this equation. Now, in general, what we have to deal with is time-ordered exponential. So you know that for an arbitrary time dependence, the evolution operator is given by the time-ordered exponential. But the fun thing is, if you actually have a periodic drive and you're interested in the evolution operator of a one driving cycle, then the micromotion comes back to itself because it's periodic and you're only left with this exponential of the Floquet Hamiltonian. So you see now it looks very similar to what you had in static systems. And that's actually the advantage of using periodic systems. So periodic systems in some sense live at the boundary between equilibrium and non-equilibrium. And in particular, if you look at them stroboscopically, then even in the lab frame, you can get this space. And you can now try to write down an ansatz for this Floquet Hamiltonian, which is an operator-valued expansion in the inverse frequency. And if you plug this here in the right-hand side, and you also insert the definition of the time-ordered exponential, what you find is that you can reconstruct the first few orders in the following way. So the leading order effective Hamiltonian or Floquet Hamiltonian, which I denote by the 0 here, is just the time average, and that's precisely the intuition that somebody pointed out 15 minutes ago. So you would expect, the time average behavior to give rise to the physics, but it's not everything. Like Sergey asked, what are the numbers, right? And I said the numbers for the frequency is about 10 times larger than the other energy scales in the problem. What this means is that you'll have to consider corrections. And so I've shown you here the first order correction, which is given by this commutator equation, and you can continue and go further. But one problem with this is that it has actually limitations. So in particular, this series here, the so-called Floquet-Magnus expansion, has a finite radius of convergence. And in fact, people have shown that it's an asymptotic series. And what this means is that you can compute the first few terms, maybe go to order 5, maybe go to order 10, and you'll get like good physics from this. But if you keep going, at some point, it's going to break down and it's going to start giving you non-physical results. And in fact, the physical manifestation of this lack of convergence is that the expansion fails to capture energy absorption. So in other words, it fails to capture resonances due to absorption of energy from the periodic drive. And we'll talk about this in a second. So, okay, I skipped that thing. So I want to emphasize two issues basically with this approach. So I mentioned that perturbative approaches like the Magnus expansion fail. So that's one kind of potential problem. And the second one is that actually, in this quantum simulation, especially if you think about solid state systems, you are interested, just a second, you are interested in ground state physics, right? But the ground state of a Floquet system does not exist. And I just want to explain very briefly why this is the case. So remember, the fundamental object is this unitary evolution operator, and the eigenvalues of the unitary evolution operator live on the unit circle. So now if you want to define the ground state, you have to figure out how to select one out of these many states, and this should be your lowest energy state. But it's a circle, so I can cut open with the purple scissors, I can cut open with the cyan scissors, I can cut open anywhere I want, right? And I don't know where to do it, so it's ambiguous. And that's why people say that the Floquet ground state does not exist. And this actually leads to problems with the simulation of ground state physics, right? Because if you want to simulate ground state physics, but you don't have access to the ground state, then what do you do? I won't tell you how to go around this problem today, but I will discuss this tomorrow in my talk because it's a little bit more technical. And those of you who are interested are most welcome to join. There's a question.
Just to understand, slide earlier, you wrote an expression for HF, HF is 0.
That's right.
So
yes, actually, that's here.
No, a slide earlier.
A slide earlier.
In terms of this E of T. Yeah, that expression.
This expression is exact.
Yeah, that is exact.
That's exact.
But your point is that generally that E of T is not known.
Correct.
That's why we need this expression.
Precisely. That's precisely right. Okay. Other questions? Yes, please.
Can you explain the physics of the ansatz? Like, why we have this high frequencies, but like each term is of this order of inverse of the frequency?
So as I showed you in the movies, whenever the frequency is high enough, this is when you get to see interesting physics, right? And what we also saw is that if the frequency falls below some critical threshold, then we lose the effect. So what this tells us is that we need to figure out an effective description for the physics at high drive frequencies. So naturally, what you want to do is you want to expand in the inverse frequency. But this is now an operator, and so you have to do an operator-valued expansion in the inverse frequency. So it's something like a Taylor series, but for operators that you're doing here. And then there's all these questions about convergence, radius convergence, etc.
And also, another quick question is, in the literature, there was discussion on Magnus expansion. So the Magnus expansion, high frequency expansion, they give exactly the same results, or they are slightly.
Yeah, so that's a good question. It's a technical question. So what you see here is the Floquet-Magnus expansion. Now there's an alternative expansion which is called the Van Vleck expansion, which is the same thing. It's also an expansion in the inverse frequency, but it's done in a different basis. And it has a slightly different form if you look at it, and we can discuss offline the details. But they're equivalent. So the order of the approximation, it doesn't matter which expansion you choose, they're going to give you the right result. And in fact, there's even one more expansion, but I didn't want to overburden you with technical details. All right, good. So once again, tomorrow we'll talk about how to define the Floquet.
Could you come to issue 1? So somehow when you have this approximation of this Magnus expansion, is it relevant to the symmetric property of the Hamiltonian or something like that?
No, actually, this is a good point. Floquet theorem applies also to non-symmetric / non-Hermitian Hamiltonians. So all you require for Floquet's theorem is linearity of the differential equation and periodicity in time. That's all it requires. So even non-Hermitian systems would have an effective description. This effective description is going to be some non-Hermitian Floquet Hamiltonian, and you can actually study this and you can analyze, stability there as well in this way. Actually, in this application of the limit cycle that we had, this is what happens there. So you can basically determine the stability of the limit cycle. Okay, great. So, okay, I spent most of my time talking about the engineering of this. Now let's see how far we can go. But the question already was brought up, how stable are those states, right? So in particular, there's a big issue with periodic drives, namely that they cause generic interacting systems to heat up. And we all know this, right? Like if you put your lunch in the microwave, it's going to be exposed to a high frequency, microwave drive, right? And then it's going to start heating up. And so physically, this is a manifestation of the fact that energy is no longer conserved. So if I look at the Hamiltonian at two different time points, it's not going to commute with it. And the question is now, is this stable? So suppose now, just for the sake of an argument, that we look at an interacting system. So this is a non-integrable model. So we can claim it's a generic system, which is somehow periodically driven. The details are not important here. What you should note is that there's local interactions between the spins, and there's also like some spin flip terms, which are also local. Another point is that whenever you have local interactions, then heating or energy absorption in these periodically driven systems is actually exponentially suppressed in the driving frequency. Here's what I mean by this. This is a time periodic Hamiltonian, so maybe a good quantity to look at is the average. So I can take the average Hamiltonian, I can evolve my system exactly with this time periodic dynamics, and I can just measure this average energy. And this is going to be some function of time. And what this statement says is that this function is actually, it might grow exponentially, so you will absorb energy fairly quickly, but the rate at which that happens depends parametrically on the frequency of your drive. And the faster you drive, the slower the rate of absorption is. And you basically see this here in that picture. So on the x-axis, I'm showing you the time in units of the driving cycle. So 10 to the 2 means 100 driving cycles, 10 to the 4 means 10,000 driving cycles, etc. On the x-axis, I'm showing you the energy, and then the different colors denote the driving period. So for instance, if the period is very small, it means, if the period is very large, it means I'm in the low frequency regime. Then my system starts absorbing energy right away, and then it gets to this maximum possible energy that it can get for a spin system, which is normalized in this case to 1. But then if I start lowering the driving period to smaller and smaller values, then you see that energy absorption gets suppressed, and in fact, it gets suppressed on a log scale, so it gets suppressed exponentially. And if you say, well, energy is just one observable, maybe you happen to hit like a specific observable, what about other observables? Then you can also look at the entanglement. So this is the entanglement of this spin chain with respect to half of the chain. This quantity only knows about the state. It doesn't know about any observable. Therefore, whatever holds for the entanglement holds for all observables you can imagine. You can see here you start from a very low entangled state. And then if you're at high frequencies, you go into this long-lived plateau here, this prethermal plateau. And so, you can stabilize your system up to, thousands and thousands of driving cycles. And not only that, you can control by just going with the frequency by a little bit, you can extend exponentially the duration of this plateau. And this is what people, then use in order to study the physics. So by this time in a real experiment, there will be all kinds of other effects, the coherence effects, etc., that will kick in, and that will, that you have to worry about before, like this will kick in. So,
we have a system gap or that means
I didn't get the question, sorry.
Means that you want to increase the frequency to reduce the heating.
Yes.
And is it depend on also if the system is gap or gapless?
It does not.
It does not.
It does not.
So for example, if I have the free electron and you microwave, you can heat it up, whatever the frequency that you have.
Well, so the idea is that if the frequency is much higher than the energies at which actually let me explain it in an intuitive picture, and then if this doesn't answer your question, then we come there. So here's my spin chain, and I'm showing the spins here, shown in the chain. And like I said, there are like these processes which cost energy J, which are nearest neighbor interactions, and then maybe you can have like these spin flips, right, from the single particle. Now, suppose that you're in the high frequency regime. This is when you get like this suppression of heat. High frequency here means that the frequency is 10 times larger than the interaction strength. What it means is that you actually need to flip 10 of those pairs in order to accommodate for the energy of one driving quantum, right? And so what this tells you is that this is a very high order perturbation theory process. And if you do the math, you actually see that the energy absorption, the probability amplitude, if you wish, for this process to occur in like a Fermi-Golden rule type calculation is going to be exponentially suppressed. And so that's completely generic for any kind of system that you have. So it basically relies on the fact that you bring your system sufficiently far away from resonance. So you far detune it. And it's safe, and it doesn't matter how strongly interacting your system is, how ergodic your system is, it's always the case. Note that there's a price to pay. You just have to wait long enough, and then the system will know that it has to absorb energy, right? But it just happens much, much later in time. Did it answer the question? Okay, great. And like I mentioned here, so there's like this long-lived prethermal plateau. And in fact, the physics of this plateau is described precisely by these effective Hamiltonians that I showed you on the previous slide. So this is where they come to use. Now, the reason why the expansion breaks down is exactly because of this long time physics that leads to heating, which is actually not captured by the high frequency expansion.
Is there an exponential there in
well, so that you don't see from the simple argument, but like I said, you have to do accounting, right? So you fix your frequency, you fix your coupling J, and then you say how many quanta of the drive can I accommodate, right? And so you see that this is basically, it's in this case, if it's 10 times larger, it's going to be 10. If it's 100 times larger, it's going to be 100. And then you basically have to resum these processes. And in the process of resumming these processes, you essentially arrive at the exponential. If you want to know exactly how that works, there's a rigorous mathematical bound on heating, which is this, and it relies on the Lieb-Robinson bound. Okay. So basically, the idea is that you cannot delocalize information faster than than what's allowed, and it also relies on the interactions being local, etc. Okay, but now I wanted to say where this heating comes from. And so the idea is the following. So every now and then it can happen that two of these quasi-energy states actually come very close to one another on the unit circle. And then if you look at them, but you want to look at them in terms of their average energy, so not in terms of their quasi-energy, then you see that these two states look something like that. So what you see here is that there's a peak at a certain energy, and then there's another peak at an energy that's precisely away by one driving quantum. Sorry, capital omega is the same thing as little. So these are so-called resonances, but you see each of these lines corresponds to one state. So these are resonances between many body states, and it is these resonances that in the long run lead to the delocalization of the particle in energy space and therefore to heating. So these resonances occur at very late, so they're always there, but their effect becomes important at very late times. And it is these resonances that lead to the breakdown of the high frequency expansion and ultimately to the heating of the system. So again, when you see that the expansion doesn't converge, there's a physical meaning of this, and the physical meaning is that there's heat. So this is what you cannot capture with a simple description. Okay. So, but why is it interesting, to study this kind of prethermalization, right? So why should we care about this? So first, as many of the talks in this workshop, are reporting on. It's interesting because it helps us to investigate the onset of chaos, the onset of ergodicity, but also thermalization. And one example is this kicked top that some of you might have seen. So this is a very simple example. It's maybe a prototypical model to study in experiments quantum chaos. And this is an experiment from 2009 where they basically mapped out the phase space, and you can kind of see the stable, the non-chaotic, and the chaotic regions of the system in the semi-classical limit. Now, I motivated the whole story by talking about Floquet engineered states. It is very important that we know how long can these states live for, right? So that we can actually use them. So that's another example. But I also mentioned this idea about quantum computing, and so let me give you a flavor of how heating is related to simulations with quantum with digital simulating devices. So suppose that you're interested in the physics of this model here, so that's the same model that we had before, where we have like a nearest neighbor Ising interaction, some Ising field, and then some X field. And I want to just add these two terms together. And so this is the physics that I want to simulate in time, but I want to simulate it on my digital device. And one way to do this is to use the so-called trotterization algorithm, which basically goes as follows. I'm going to chop time into small pieces. And I'm going to rewrite this left-hand side essentially, like that, which is essentially, which is going to give me, exactly. Which is going to, okay, so this is, I think I missed a sign. So this has to be an equal sign, right? Because that's still like the same physics, but then the approximation comes here on the right-hand side, where I'm basically splitting this exponential into two separate exponentials, right? That evolve independently. And so I'm simulating the dynamics of the system that I want to study by successful applications of these bursts, if you wish, of different Hamiltonians. And the reason why I do that is because I can easily simulate these on a quantum device. So this is the picture here with the correct color coding. So in green, you have like the X gates. These are single particle gates. So I apply them, on my quantum, on my qubits in this case. Then after I'm done with the application of the X gates, I get to the Z gates. And the Z gates all commute with one another, so I can first choose to apply the nearest neighbor ZZ interactions, and then I can apply in red the on-site Z terms. Once this happens, the whole circuit repeats, right? And I get like a periodic structure. And as you can see now, this very natural formulation of a problem of simulating a static quantum system on a digital simulator amounts to understanding the physics of this periodically driven system. So now the question is, what is the manifestation? When does this approximation work, right? And when does it fail? So let's check this. So these are results done by Markus Heil in the group of Peter Zoller from a few years ago. What you see here is, the magnetization. So that's essentially the, I think it's the X or Z magnetization. I'm not sure. As a function of time, and the different colors here are essentially different values for this parameter tau that I'm using. And what you can see is that essentially the smaller the time step becomes, the more and more accurate the dynamics. And this is just a zoom of that physics. But what you also see is that if this number becomes too large, then this is the orange curve. Then the accuracy is very, very poor, right? And so they have looked at the magnetization as a function of this small parameter, right? So this is parameter that I have to set. This is my time step for the Trotter revolution. And what you see is that as a function of the system size, there's a regime as a function of tau when tau is small. So that's the high frequency regime where, magnetization is stable and you get like good approximations. As you increase the system size, everything looks good. And then there's this shaded regime where all of a sudden the magnetization at long times goes down to zero. And what this means is that your approximation completely broke down, and so what you're simulating is not the correct physics. And the same thing was investigated in this paper by Ikeda et al., where they are looking at some heating measure. It's not important which one it is, but this is basically telling you, does your initial state heat up at very long times, again, as a function of the same driving period. These are now slightly bigger system sizes, so they went all the way up to 30 spins. And what you see again is that there's this region where the system effectively looks like it doesn't heat up, and it doesn't heat up to exponentially long times. Whereas if you wait a little bit longer, then all of a sudden it starts heating up, and then the regime breaks down. So all of this is to show you that understanding prethermalization is important, not just for the simulation of engineering the states, but it can also be important to understand chaotic behavior, ergodicity, thermalization, and it can also be important, in these digital platforms to simulate dynamics. So it's a fairly wide concept. All right. So time is closing towards end, but I have a little bit more to tell you. We have to decide how to proceed from here. But there was a question maybe for that.
Sure. Right. So by thermalization, you mean the regime where it's not heating up too much, meaning which is close to the Hamiltonian regime, right?
Precisely. Yeah, and that's the regime where the expansion works. That's the regime which is exponentially protected by the driving frequency, or if you wish, by the small driving period. What I'm showing here is that this exponential protection actually has a physical meaning and a physical interpretation in terms of these algorithms to simulate the dynamics of, to simulate analog dynamics on digital devices. Keep going. Okay, good. I'll try to make it fast. All right. So we've seen now that we can use periodic drives for to simulate interesting physics. Then there was the question: are these states actually stable that we can engineer? And we basically showed that maybe they're not completely stable, but they're exponentially long-lived. And the next question that you have here is, how do we actually control the states of these effective Hamiltonians? So the fact that I have managed to engineer an interesting Hamiltonian which supports a state I want to study, and the fact that this state doesn't heat up on my timescales of my experiment, doesn't mean that I can study the state, because I need to figure out how to place the population into that state. And that's the question of quantum control. And the state of the art is, as usual, just adiabatic variation of model parameters. For instance, you slowly change the amplitude or the frequency of the drive. But there are actually issues with that. So let me explain to you what the issues are. Suppose you have a static system, and let's say that the static system is governed by some Hamiltonian, which depends on some control parameter lambda. And now we know that if this is a simple system and we initialize, let's say, the system in the ground state, and we tune the parameter slowly compared to the inverse gap, then at later values of time, we find the system at the instantaneous eigenstate corresponding to a later parameter. And that's basically, the statement of the adiabatic theorem, and this is known as so-called Landau-Zener cross. But now we have a periodically driven system. So if you have a periodically driven system, you can imagine two states that in principle are very far away. So they are, let's say, two frequency apart. So the state here differs from the state there by 2 photons, right? So L here denotes the number of photons. Now, if I turn on the periodic drive in such a situation where I potentially can have a resonance, what happens is that these two states are basically brought together. This was essentially this idea that I can shift my quasi-energies by integer multiples of the driving frequency without changing the physics. But now there's a crossing. And as we know from quantum mechanics, whenever there's a crossing, a gap will open. And this gap now is due to the absorption of a photon. And in this case, you absorb 2 photons from the drive. So let's see now what happens. Let's say that we start the dynamics here in this state where there's, let's say, L photons in the system. Now, if I would naively follow the same description as in static systems, I would find my state at later times in this state. But what's that state? That's the state that have absorbed 2 photons. And therefore, here I have basically absorbed 2 quanta of energy. My energy has grown up. And this is, of course, not the proper way of defining adiabaticity with respect to this effective system. You can do this formally mathematically, but physically what it means is that you absorb 2 quanta of the energy, right? And so that's a problem because resonance leads to heating, as we have seen. And so in reality, what happens is that you might have actually the 2 types of crossings that we see here. So the standard crossing and the photon absorption crossings, you can have them both in the spectrum of your quasi-energy system. So this is now the quantum version of this Kapitsa pendulum. I call it the Kapitsa oscillator. What I'm showing you here is the quasi-energy spectrum as a function of the control parameter, which is here just the strength of the periodic drive. And what you see here on the one hand is this green crossing between these states that I've marked here, which it turns out to be just a standard crossing, where we know that we have to go very, very, very slowly in order to not to excite to the nearby energy state. But at the same time, there's this crossing here, and this crossing happens to be a photon absorption crossing. And we know that here, if we go too slowly, then eventually we go into the blue state and we heat the system up, right? So there's this competition that if I go too slowly, then I don't know which way to move. And so here on the right, I'm showing you the excitation probability as a function of the speed at which I'm changing my parameter lambda. So what you see is that if I go too fast, then I'm not adiabatic. So first of all, what does adiabatic mean on this? So this is a log scale. So adiabaticity means that the excitation probability is proportional to the speed. And so what you should find here is a power law, right? Now, if I go too fast, I violate adiabaticity in the standard crossing as expected for a fast process, and therefore I start deviating from the power law. In a normal static system, you would expect that as you lower the frequency, you start to become adiabatic. And indeed, here it looks like it's the case. But if you keep lowering the frequency lower and lower, at some point, you hit the photon absorption resonance, and then, you cease to be adiabatic again. And so you see now that there's like a regime at very high frequencies, a regime at very low frequencies where the system is not adiabatic. And so the best you can hope for is these regimes in the middle. And the fact that it exists in this simple system, is more or less by chance. If you take more complicated systems, these regimes might not even exist. And this is why we say that, there's the adiabatic limit, which is basically pushing the speed to zero and then finding, the power law in this regime does not exist for the states of this effective Hamiltonian. So that's the problem. This is a problem now for experiments because, the state of the art is indeed this adiabatic variation. Now, in experiments, there's a second problem that the time scales actually take longer than the coherence time. So you can only have your system to be coherent for, that many cycles, right? And if you don't manage to prepare the state quickly into this Floquet state, the system quickly into the Floquet state, then you cannot do the experiment anyway. And then, as I mentioned in theory, there's a problem with the existence of the adiabatic limit, but there's another problem in theory, which is that the control field now would be an arbitrary time dependence. I'm ramping up something, and so I'm going to break the periodicity of the Hamiltonian, the time periodicity of the Hamiltonian. And I start asking the question now, does Floquet theory apply in the first place, right? And strictly speaking, it doesn't. And so how do we actually solve this question? So at this stage, there's a question, how can we develop non-adiabatic techniques? And so this is where, I would have introduced the shortcuts to adiabaticity, but I think at some point, we have to move towards the end of the talk. So if you're interested in this, in the second part, the idea was that I tell you about how to use counterdiabatic deriving in order to speed up these processes. And in fact, one can do this, but this is going to take maybe 15 minutes, and I don't want to, take it too long. So I think at this stage, I can try to go to some of the summaries. And well, okay. Okay, and maybe if you guys have questions about like the control, you can ask me afterwards, and we can have like more discussion. I'm more than happy to explain. So basically, the idea is that we have these periodically driven systems, and what they do is they can change the properties of quantum mechanics. And therefore, people have realized that one can use them for quantum simulation. So you can use the periodic drives in order to engineer Hamiltonians and states of Hamiltonians that you cannot reach otherwise in static systems. But then you realize that these are non-equilibrium drives, and therefore they can lead to energy absorption and heating. But one interesting feature is that if your driving frequency is sufficiently high, then this heating timescale is going to be exponentially suppressed. And what this allows us to do is it opens up essentially a long, exponentially long prethermal window where the physics is precisely governed by our effective Hamiltonian. So we can actually access a stable state for sufficiently long to actually study it. And what I didn't have time to tell you about is how to actually transfer the population into that state. I only told you that there's this intrinsic problem of using naive techniques such as adiabatic drives for periodically driven systems. And what we have done is we have extended these adiabatic drives using shortcuts to adiabaticity to time periodic drives, where essentially you can imagine ramping up the frequency of the drive or ramping up the amplitude of the drive or chirping the frequency of the drive. Or maybe you have a system that is periodically driven and you want to apply an external field and change that. And so you can actually do all of this with counterdiabatic driving, with shortcuts to adiabaticity by defining a variational principle and a gauge potential. And like I said, I'll be very happy to tell you about it offline. I just want to briefly mention what I will talk about tomorrow. So you can see this is the amplitude, the frequency, and the external parameter, but periodic drives also have phase. And tomorrow I will focus on the phase of the periodic drive. And what I will actually show you is that if you consider changes in the phase of the periodic drive, everything I told you about Floquet theory today can be derived from the adiabatic theorem. And that's a little bit disturbing if you think about it, because adiabaticity is about slow variations of parameters. And I was just talking about very high frequency periodic drives. And so this question, how can this actually be? And if you come tomorrow at 11, I'll show you how this can be. And not only how this can be, but how we can use this in order to solve the problem, with the resonances that are not captured by the effective Hamiltonian. And we'll solve this using counterdiabatic driving. And not only that, but it will help us to resolve also the problem of defining the ground state for periodically moving systems, which is a big outstanding issue, but we now know how to understand it, I think, much better. All right, so with that, I'd like to thank you for the attention, and I'd be happy again to take any questions about how to control the systems if you're interested.
Yeah. So one question, you talk about coherence types. Are these dependent the periodic driving? If you have a system coupled to an environment, to what extent can you just use to send the coherence times of the system, which is not clear?
So by the environment, you mean the periodic drive?
No. I have some auxiliary degrees of freedom, like a path of oscillators.
So what I
for system to be as
So what I meant there is the following: suppose that I have your system, right, coupled to a drive, etc., but which is not periodically driven, right? It will have some natural time scales, right, at which the state is going to be coherent. This has nothing to do with the periodic drive. This is just, it tells you how good of a simulator, you have, right, in the lab. You have that time scale, and this actually poses a limit, right? And that limit forces you, now in the presence of the periodic drive, right? What I've shown you also in the presence of the periodic drive is that the time scale to absorb can actually be pushed to exponentially long times. So what this means is that the time scale to absorb from the periodic drive is going to be beyond the time scale for your system to decohere. And then the question is, can you actually do the preparation faster than your time scale decohere? So this is why you would need a shortcut.
I was thinking on the theory of open quantum system, your system embedded in an environment. If you derive a master equation, it is, typically you do it for a static Hamiltonian. Now you are driving your system very strongly.
Yeah.
I wonder to what extent is just
it's going to go through. It's going to go through, and
for other drivings, it doesn't go have to account for this. Yes, this is
the high frequency. The high frequency is exactly the high frequency is a point here, because and the mechanism is going to be very similar to the one that I explained. So if you want something to happen with your system because of the drive, you need to absorb, right, energy. But if your matrix elements to absorb energy are suppressed, and we know that they are suppressed without the coupling. So for as long as you manage to stay away from the resonance between the coupling of the system and the drive, I think you're all safe here at these scales. Yeah.
Novel's point is very interesting, actually, because of course there's many body effects in your jump operators. So if you look at many body jump operators, I don't think it's as obvious as you say, although I like it qualitatively, but it'd be nice to walk through it. So I just comment on that, and then I have a question. But yeah, because people.
So just a quick comment on that. So actually, if you really want to have like a proper derivation of this, you have to worry about one other thing. Is the master equation, like that, the right description of this. And for this, you need to make sure that the dynamics remains Markovian, and there's a number of examples where this is actually not. So whether like just writing down the Rimblad equation is the right starting point is already something that you have to worry about.
Yeah. Okay, and then probably totally obvious to you, but I'm sorry, I just didn't follow this point. So for trotterization, it seemed that your exponentially long times were not under your control, the way that you showed the plot. So could you come back to this plot and just explain to me why every single trotterized quantum simulation in the quantum computer is not going to fail according to your predictions?
Right. So
it's this picture on the right, yeah. So it's
picture on the right.
Independent system size. And so, sorry, where is your control? Is it in the H tau down there? Or?
So okay, so in this case, there is no control of the system, right? What we have is we have a system that just is static, and however, we are trying to approximate its time evolution through this digital drive. Okay, so there is no parameter that is changing with time here. Everything is fixed. So in particular, the duration, your driving period or your driving frequency is fixed. Okay, and that's what's shown here on the x-axis. So basically, each of these points are different experiments, if you wish. So you fix your time step, you apply the trotterization, and then if your time step happens to be below that threshold, then you basically don't heat up. And what this means is that you can simulate the correct dynamics. Of course, There might be like a small, a small deviation, but this deviation is under control. If you go above this threshold, then your approximation is no longer under control. Basically, one thing that I wanted to mention, but I didn't, is that this factorization of your evolution operator is just the simplest thing you can imagine, but you can actually go to higher order. If you go to higher order, this curve will come closer and closer to the dashed line, which is the value that you actually want to simulate, right? But it will only come closer and closer in this regime. So this is the regime where you might hope to have. In this regime, there's basically no hope.
So to summarize, if you have a small enough time step, you're fine.
For this specific model, yes. And the reason why you're fine is because the energy absorption is exponentially suppressed. That's the real reason. In fact, people are still fighting over whether you've waited long enough here, right? Because here you have gone to something like I don't have it anymore, but I think it's something like it's hundreds of thousands of cycles, right? Like very huge number of cycles. But you can only simulate so long because you don't have access to the infinite times, right? And then there are all kinds of skeptics that say maybe you just haven't waited long enough. But then for practical purposes, which is what we care about, right? It's all good. The only thing you have to know, you have to be careful about is that you don't start from the wrong value. Because if you start from the wrong value, there's no hope.
And like in experiments, how do you apply this periodic drives? Like you apply periodic pulses.
So that depends. What kind of experiments do you have in mind? Yeah, if you have a trapped ion, what you have is you have lasers, right? You have like electromagnetic waves, and then naturally these are waves, so they are oscillating, right? And so you can apply them from different directions, and with this you can couple to to your particles, and then ultimately get the whole thing to start stirring, right? That's one way. For cold atoms, it is similar. It's again, or for cold atoms, actually, there's different ways of doing it. So you can use the lasers, and then you can have like these Raman transitions in order to induce the effect of the periodic drive. But you can actually use like a so-called piezo elements. So these are like mechanical devices, and they oscillate very, very, very fast. And so essentially, we have like fast oscillating mirrors, and then through these fast oscillating mirrors, you generate an additional very high frequency modulation of your optical lattice. And so you have, for instance, a term in the Hamiltonian that's proportional to the atomic density, and then that modulates it. Another way of getting it. In superconducting qubit devices, you typically do something like that, right? Like fertilization. That depends now on the platform system. Yes, typically electromagnetic drives or some mechanical forces are the way to go. This doesn't mean that you cannot have other ways.
But will the time scale matter? Like, let's say you are applying it interrogate, like the time scale.
Of course, that's this plot here, right? So the time scale of the gate, right, is precisely this stuff. So if this is not small enough, we're dead, right? But the whole point is that it doesn't have to be fine-tuned to any point, right? So there's an extended region in which it's still okay. More questions today?
You mentioned at the beginning the ball trap and the Earnshaw theorem, and how this was resolved using these drivings. Do they have simulations when they trap ions or these ball traps?
Oh yeah, this is.
They have also some. Can you comment a bit on it?
I'm not like a great expert on trapped ion computing, but yeah. So trapped ions currently are one of the 3 leading AMO platforms for quantum simulation. So next to the ultra cold atoms and superconducting qubits. So you might have heard about Google, IBM, that superconducting qubits. You might have heard about Michel Looking's experiments in Harvard. So this is like neutral atoms, right? Then there's the trapped ions, right? And trapped ions are considered for quantum simulation. And in fact, somebody mentioned the gate. So the gate precision for trapped ions is the highest. And the way that they're actually trapping their ions so that the ions don't just fly away is using this trick with ball traps.
Yeah, the question then is, do we have a problem with
all these platforms have problems with heating. It's just a question of what time scale does it kick in. Okay, so maybe Yeah, maybe to turn your question around, and this is not just the trapped ions, it's also the ultra-cold atoms, not so much the superconducting qubits, but if you think about the optical lattice, the optical lattice is also a high-frequency field, right? And so even without any external periodic drive, if you just put atoms in an optical lattice and you just leave them there, at some point they'll fly away because they will heat up from the periodic drive. But similar to what I was explaining today, these time scales are actually pushed to very low. So you can introduce a secondary drive and then play with it in order to do the engineering. So it's always, a matter of time scales and energy scales. But as long as you can push them apart by 1 order or 2 orders of magnitude, I think experimentalists are happy. In theory, we speak about the high frequency limit, but this thing doesn't exist. Like I said, what we really mean is 10 times larger than some reference scale.
So I have 2 questions. One question regarding these figures. So in principle, we know that learn from you, this Floquet driving will be very powerful to engineering Hamiltonian. My question is for instance, whether you can use this Floquet driving to simulate the two-body interaction, like nested commutators.
Absolutely, people have done this. Now, let me just clarify something. So if you start from a non-interacting systems, the driving is not going to bring in interactions, right? So there's no free lunch. But if you start from a system that interacts on site, then you can use periodic driving to find interaction terms that are, for instance, nearest neighbor. And people have done this. And this goes using these, Bessel functions that you can tune some terms to 0 and then they don't appear, but then other terms eventually start dominating, and that's what you try to engineer.
So in principle, you can simulate X, Y, Y, Z, F.
Yes, and this is so because I know that you're doing work like on counterdiabatic driving. So this paper by my colleague Peter Kleiss and Marin Bukov, they use periodic drives to simulate the adiabatic gauge potential. This is done through these nested commutators in higher order terms. So basically they figured out that nested commutators are identical, and so they can implement a non-local gauge potential through a local drive periodic. That's how that works. Same mechanism.
My second question regarding this to the system normalization. For instance, when you apply the high frequency driving, do you see any influence of approximation or confidence?
Yes. So the rotating wave approximation you can think of as the leading order time average Hamiltonian, and that's what you get actually from the high frequency expansion. But then there will be the 1/omega direction term. And these terms, they become important anywhere in experiments because, like I said, you never work with infinite frequencies, but you always work like it's finite energy scales and time scales. And then you have to take them into account, because if you don't take them into account, for instance, you will either be tuned away from the resonance, or the resonance will shift a little bit, and then you won't be able to control it. Or if you want to prepare states, then it's even more. Thanks.
Well, for the case of dissipative dynamics, with the driving, there is a certain steady state, and thus a periodic driving can change a steady state or modulate it.
Yes, it can, and people have looked into that. So you can use this to open systems, again, provided that your description of the open system is static. So you have to worry a little bit about the assumptions there, but it will go in a similar way. This is a whole different business and a whole different talk there, and it's actually more involved than isolated systems. I decided to focus on isolated systems first because they're simpler, right? And second, because there's a lot that has been done with them. And there's still a lot of open questions, like for instance, these control questions and how to manipulate them in the presence of the periodic drives. Like I showed you, there was this problem, right? That have to resolve working on this.
I guess in experiment, if you do this trapped ion experiment, probably the column plays some role there. So I'd like to have your some comments that if the there's some certain parameter region where we need to consider this the formal stage or.
Yeah. So that's right. So there will be the phonon mode. So unlike optical lattices, for phonons you will keep additional modes. When that happens, you'll actually see these resonances that I was showing, right? So this is an extreme case, right? Yeah. Where many states of your system kind of talk to each other via, you can't see from there, but the distance between these peaks is precisely 1 driving point. So if you tune your driving frequency to be resonant with the natural frequency of the phonon mode, bad things will happen. So you will start absorbing in this external system.
You mean you have a standard crossing and the photon crossing, probably the phonon. Yes.
So exactly. Like I said, there's 2 types of crossings, right? So there's the typical standard crossing without the drive, but then there's also the crossing from the photon, right?
Yes.
And in this case, the one without the drive will be the phonon crossing. The one with the drive will be the photon crossing, and then you'll have both photon and phonon crossings that you need to be careful about. Otherwise, you will absorb. If you absorb, you lose the state, right? Because we're interested in these low-lying states, whatever low means. I'll tell tomorrow what low means, right? But we're interested in these states, and if you just go to some highly excited state, you just don't see physics.
Last question.
Hello. In the case of the prethermalization of the entanglement that you showed, do you know what are the properties of the effective Hamiltonian, which is not dependent in time, which give rise to this time scale so large?
So, okay, the effective Hamiltonian doesn't know about this time scale. So this time scale is due to resonances, and resonances are beyond this effective description.
So it doesn't matter in what order you got the approximation.
It doesn't matter what order the approximation. Of course, there's this caveat that if you go with the approximation that's a very crazy order, and the series is asymptotic, going to destroy. But let's say that you go to the first few orders, then if you just do a quench to this effective Hamiltonian, what will happen is that you will go to this plateau, and then you will stay in this plateau forever, right? And this is by the eigenstate thermalization hypothesis, because this guy here is a local Hamiltonian. It will be leading order, just the sum of these terms with static couplings, right? There's a time average place. But then the first few corrections will have a couple of massive commutators, so it might be localized a little bit, but quasi-local. And so the eigenstate thermalization hypothesis will apply. And so within this effective description, you will never get out of the plateau. The only way you can get out of the plateau is if you know how to get the resonances, but the expansion doesn't know about the resonances, and therefore you can't actually describe it. And so the physics of these resonances and how to describe them is actually an open question. So people have seen them, but they don't know what's a good effective model for them. Yeah. And that effective model should know about this test. We can keep them going if you get this one. I was paying.
One quick.
No. So I guess there's time until lunch anyway. I'll start dealing.
So this high frequency expansion is like asymptotic expansion. So usually when in many cases if we do asymptotic expansion, like the actual convergence radius is actually 0, but they are very effective in the sense that if you just take a few terms, then the precision is really high.
Yeah.
But then the feature of asymptotic expansion that if you include in more and more terms, and then you see that the accuracy is going down. I'm just wondering, do you observe this?
People have seen that, yes.
I mean,
people have seen
this
Floquet. I think in the example that I have in mind was done by Takashi Mori, so far away from here, I guess in Japan. Some of you might know him, and I think the numerics, if I remember correctly, show that if you go up to order 18,
okay,
for that specific model, everything was looking better and better and better. And then once he crossed 18 and went larger, then he started seeing that it becomes worse.
So this the critical
order,
yes. 18 is large.
But no, I mean this 18 is is specific to the model that he studied, which I guess was one of these spin chains again, right? That we love studying. So if you have a different system, you have to investigate it case by case. You don't really know when this is going. Yeah. But I want to emphasize that the asymptotic expansion is a property of the many body systems. Now you can take just the 2-level system, And in a two-level system, you can show that there is a finite radius of convergence for your series. And if the frequency becomes too low, then your series will still not go. Again, that's the regime where the frequency becomes comparable to the energy levels, and you start, seeing resonance. Even if you have two levels, it's enough to see resonances, and then your expansion will break down. And the intuitive way to think about it is, if you just have a two-level system, think about the eigenvalues of effective Hamiltonian for a two-level system. It will feature some square roots, right? But the square root is a function that has a finite radius of convergence, right? And that's how this all comes about there. It's a very simple way. Thank you.
Right, then let's thank the speaker once again for this wonderful.
Apologies that I didn't get to the control part, but there will be more of this.
You have dinner from